Okay, let's carry on from Monday's lecture. Sorry for canceling class, the live version of it. It's just too slippery and too snowy to take a chance to going on the streets and highways of Kelowna. Not too sure why UBC didn't cancel classes on our campus, but I did. So I want to begin today's class by looking at an article that was published in New Scientist. So New Scientist is a popular science magazine that comes out of Britain, and in this article that I want to talk about, we're going to look at the various numbers that are thrown around concerning global warming and human-caused climate change. So the title of the article is Uncertain Certainty. So the purpose of this article was to clear up the confusion that exists around the numbers that are presented regarding human-caused climate change. And much of this confusion deals with the fact that there is no standard way of measuring climate change. For example, there is no standard starting point. Different scientists, different agencies use different starting points, and then there's also the problem of endpoint. So let's look at the question: how much has the planet warmed already? So there's all kinds of values floating around. One of the things that these values use are based on is some sort of baseline, and then that baseline is usually a period of time, not just one single year, but at least a 30-year normal or more, maybe up to 50 years of data averaged, and then of course you have to have an endpoint. NASA, in some of its publications, talk about pre-1970 baseline. So they estimate, because there really isn't meteorological data that goes back that far, they estimate what was the average temperature of the planet's surface at that time, pre-1700. If you use that baseline, you come up with a level of warming, global warming of approximately 1.2 degrees Celsius up to 2017. So if we were going to change the endpoint to 2023, we'd probably add another 0.3 degrees. It's pretty close to 1.5 degrees Celsius of warming. Another baseline that's commonly used is 1850 to 1879, a 30-year period at the beginning of when meteorological instruments were actually measuring temperature, precipitation in the United States, parts of Canada, and Europe. So I'm going to show you a slide that has that baseline. And it comes from, it shows the fluctuations in monthly temperature from 1850 to 2020. The IPCC uses a 51-year period baseline from 1850 to 1900. If you use that baseline, there's been about 1.126 degrees Celsius of warming up to September 2019. So notice once again I changed the endpoint from 2017 to 2019. So here is this temperature record, and it's a record that's produced by University of East Anglia in the UK, and it has this code name HAD-CRUT4. So we can see the monthly fluctuations from the beginning 1850 all the way to the end of 2020. And I put several different baselines on here. So there's that baseline, that 1850 to 1879. I also put a baseline that is based on the average temperature from 1901 to 2000. The green line represents a baseline, another baseline that NASA likes to use, 1851 to 1980, and that baseline was picked because that's the period before global warming took off for its second phase in around 1975. I've also put a baseline for 1861 to 1990, and then finally the purple line on the top represents a baseline from 1981 to 2010. So if you see a publication that is using let's say NASA's 1851 to 1980 baseline to measure how much global warming has taken place, you need to recognize that prior to that there was probably about 3 degrees or 0.3 degrees of increase in global temperature from pre-industrial. So be very, very careful with the baselines. Here's another graph. This one I just created, and the endpoint of that graph is the year 2023, and you can see that 2023 is the warmest year for this whole record, going back to 1880, and the last sort of maximum global temperature prior to 2023 occurred in 2020 and in 2016. They were tied. You can see at a global mean temperature of 15 degrees, and we just beat those two previous records by about 0.2 degrees Celsius in 2023. So once again, I put a whole bunch of different baselines in there. Purple represents 1901 to 1930. There's the gold one that is 1901 to 2000. GIS is NASA. NASA's one of NASA's normal baselines. So 1951 to 1980. GIS stands for, well, I can't remember, but in another class I'll mention it. The purple or pinky is 1981 to 2010, and then I put the baseline for the last sort of normal period from 1991 to 2020, that 30-year period, and you can see that we've had from that baseline approximately 0.6 degrees of temperature rise from that baseline, and it starts about the year 2000s. So in the last 23 years, temperatures have increased by 0.6, and that's pretty significant. It indicates that global warming it has picked up since the 1970s. Here in this diagram, I just isolate NASA's GIS 1981 to 1980 baseline average, and we can see from that average global temperatures have increased from that 30-year period about 1.2 degrees Celsius from that baseline since roughly the 1970s. So here again, we can see there's a baseline in here. It goes up to 2020. The baseline is, in this one, 1850 to 1879. And then some trend lines were drawn in, with the black representing monthly observations, the black lines, and you can see the variation from month to month. And then the orange, goldy orange line represents sort of a trend line of temperature change just based on human-induced warming. The blue line below represents natural warming and cooling, so slight increases because of increased solar output or decreased solar output may have dropped temperatures. The main dips in that curve are being caused by volcanic eruptions, with the last two being El Chinchon and Mount Tambora. But if you go back to 1883, you can see the effect of Krakatoa on global temperatures in that blue line. So not only do we have different baselines and various endpoints, we also have different temperature records available. So all of these temperature records are based on the records that exist around the world, but these records have been adjusted for missing data. So from about 1950 onwards, there's not much missing data for continental locations in between 60 degrees south and 60 degrees north. But prior to that, there was large data, sort of missing data for parts of Africa, South America. And so what these temperature records have done is they've tried to extrapolate what was going on in those areas where no data was being collected. And there's all these different agencies that do different extrapolation. So for example, one data set called GISTEMP by NASA, they have their particular extrapolation of what happened prior to 1950 in those areas. There's another data set called NOAA Global Temp, and then I already mentioned the one produced by East Anglia, the Meteorological Office. Hadley Center is the department, and that's the HAD-CRUT-4. Okay, one of the issues, another issue that exists in terms of estimating climate change is how much climate change is going to occur in the future with the addition of more CO2 into the atmosphere. And the reason why this is difficult is because we're not sure how the climate system will adjust to higher CO2. Because within the climate system are all kinds of feedback mechanisms. Some of these feedback mechanisms are positive, so they add even more warming. Some of them are negative. So we're unsure. So that's why you see a range of temperature values for what could be the potential temperature increase if, let's say, you double CO2 in the atmosphere. An example of a positive feedback mechanism could be that more warming creates more cirrus clouds, more water vapor in the atmosphere, and of course that acts as those are greenhouse sort of those factors act to increase the greenhouse effect. A negative feedback mechanism would be the development of more low-level clouds, which would reflect solar radiation back to space, an increased percentage or higher percentage of solar radiation going back to space. So in fact, that would cool the planet. Warmer temperatures increase concentration of water vapor, which is a greenhouse gas. But then we have these feedback mechanisms, negative ones, that can cool the planet, and this is the formation of more low-level clouds, which could also occur because of increased water vapor in the atmosphere. An important term that is used related to these feedbacks processes and the variation of estimates of how much global warming can take place or will take place is something known as equilibrium climate sensitivity. So how much equilibrium, so equilibrium being, finally when everything cycles out in terms of positive and negative feedback mechanisms, what will be the equilibrium temperature change if we double CO2 from pre-industrial amounts of 280 parts per million to 560 parts per million. Now, the estimate of equilibrium climate sensitivity has varied with the IPCC reports. In the first assessment report, the equilibrium climate sensitivity to doubling CO2 was estimated to be somewhere between 1.5 and 4.5 degrees. This equilibrium climate sensitivity did not change in the second or the third assessment report, and then it shrunk in the fourth report, expanded again to 1.5 to 4.5 degrees Celsius in the fifth report, and now we have we think better modeling, and in AR6 and in the sixth assessment report, and now this equilibrium climate sensitivity has shrunk to a smaller range of between, let me get this right, 2.5 degrees Celsius to 4 degrees Celsius global increase. And so that's the dark blue. The dark blue represents the 66% range statistically, and the light blue represents 100% range of the models being used. So of the models being used, and each model is tuned differently in terms of feedback processes. So there's a high end of 5 degrees Celsius in some models, and a low end of 2 degrees Celsius, with a middle value being about 3.2, 3.3 degrees Celsius of warming in AR6, the sixth assessment report, the one that I'm using primarily in this class. So we assume the time lag for equilibrium warming is a few decades, but maybe it's longer. I mean, it's going to take the ice sheets in Antarctica and Greenland, a couple hundred years to equilibrate. And basically what we're going to do is we're going to replace a very reflective surface with a darker surface, and that's probably going to have some effect on global temperature. So let's get back to looking at some of these ranges for this equilibrium value. So AR5, the range of forecasted values goes from 1 degree Celsius to about 6 degrees Celsius, with the 66% range between 1.5 and 4.5. AR6, the equilibrium, I got to back up. Oh, there it is. Equilibrium climate sensitivity is between 2 and 5, with the 66% range statistically somewhere between 2.6 and 3.9 degrees Celsius. Averaging the predictions of various climate models, there's now more than 40, we get a climate sensitivity of doubling CO2, actually of about 3.7 degrees Celsius. So yeah, in the previous slide I suggested it was lower, but this is the correct value, is 3.7 if we double CO2. Okay, here's an important question. What is a safe limit of warming? The Paris Climate Agreement, which was part of the Conference of the Parties, the COP meetings, in 2016, scientists agreed that the goal to future reduction of potential global warming should be well below the 2-degree mark relative to pre-industrial levels. So this, 2023, it looks like we're just below 1.5 by a few, a couple tenths of a degree. No, even smaller than that, by hundredths of a degree. In the end, they said, well below 2 degrees Celsius, the level that was suggested as the threshold that we shouldn't cross is this 1.5 degrees Celsius, and that's roughly equivalent to an emission scenario known as SSP1 -1.9, and I'll talk more about what these emission scenarios are that are used to try to estimate what potential global warming could be in the future. Some scientists now believe that even 1.5 is not a safe value in terms of, you look at sea level rise. 1.5 might in the end result in more than 3 meters of sea level rise. We're also seeing at this 1.5 degrees Celsius level the increased occurrence of weather extremes, whether they're temperature extremes or precipitation extremes. And examples of some of these extremes that have occurred in the last decade are right here in British Columbia. In June 2021, the end of June 2021, we had a record heat wave that where in many locations in southern BC, temperatures were broken by close to 5 degrees Celsius. Not by half a degree or 1 degree, but 5 degrees. And then later on that same year in November, we had record flooding occurring from Vancouver all the way to Hope and into Merritt. And some other things that we've seen in terms of record-breaking extremes, extremes of flooding all over the planet. The flooding also then leads to landslides. We've had coral bleaching events, species extinction being caused by extremes of temperature. So let's talk a little bit more about that 1.5 degrees Celsius limit. Okay, so scientists estimate that we'll reach the 1.5 degrees Celsius limit somewhere between 2030 and 2052. Now, the last time I taught this class last year, I used an average value of 2041. However, if you draw a straight line through the global temperatures that we've seen from 1970 onward and include this 2023, it now looks like we could cross that 1.5 degrees Celsius threshold in 2035, so much earlier. What's going on? We're still, a lot of emissions are still high in terms of how much carbon dioxide, methane, nitrous oxide is going into the atmosphere. So in 2016, the emissions were equivalent to 52 gigatons of CO2 equivalent. So equivalent means you can include methane and nitrous oxide in that. In order to reach the 1.5 degrees Celsius limit, we have to lower this 52 gigatons of carbon dioxide equivalent to 25 to 30 gigatons of carbon dioxide equivalent per year by 2030. So in 7 years, in order to limit global warming. and we still haven't seen, even in Canada, a trend of decreasing emissions. Emissions are still going up. Now there's a problem because the data for emissions of these greenhouse gases has a lag of 2 years. So what's reported this year is what occurred 2 years ago. And there have been some policy changes in Canada with the purpose of trying to lower CO2 emissions. So here we have another graph of data from there's what GIS is. Goddard Institute is GISS. So here's, I drew a best fit line from 1970 onward, trying to go in between the points and relative to the last data point of 2023. And you can see that, this best fit line suggests that 2035 is when we're going to hit 1.5 degrees Celsius level of warming. And that's relative to the IPCC baseline of 1850 to 1900, which is a global temperature of 13.8 degrees Celsius. The NASA average of 1951 to 1980 is just 0.2 degrees Celsius warmer than the IPCC 1850 to 1900 average. So I've got the two values there, so you guys can think about those baselines. How different are they? Okay, one of the biggest issues around this human-caused climate change and global warming is sea level rise, because a large proportion of our population lives at sea level. So how much sea level rise will occur because of global warming? So 120,000 years ago, global mean temperature was about the same as it is today. So about 1 degree above 1850 to 1900. It's actually a little bit warmer than that right now. So if we use paleo data, how high was sea level at that time? And that would be an equilibrium level of sea level. It was 6 to 9 meters higher than today. So that's, think of Richmond and 9 meters, that would be the equivalent of a 3-story building. So 6 meters is a 2-story building, 3-story building. You're in downtown Richmond, look at a hotel there, and the sea level will be up past the 3rd floor. Now the problem is, how long does it take for sea level to rise? And it's a combination of things. It's a combination of the ocean warming up and the water in the oceans expanding because they're warming, warmer molecules of water. And then also it's the addition of runoff from glaciers and other ice fields that makes sea level increase. IPCC projections suggest that sea level by 2100, if we limit warming to 1.5 degrees Celsius, will be somewhere between 0.3 and 0.8 meters. So it's a wide range. There still is quite a bit of uncertainty about how expansion of the water in the oceans, the seawater, and the addition of water from glaciers and ice fields, how that will change sea level. Under the worst case scenario, the rise could be somewhere between 0.5 and 1 meter by 2100. And it's estimated that and to reach the equilibrium, we might be looking at 1,000 years of sea level rise, even if we stopped the warming of the planet right now. So sea level rise is an extremely long lag time. And the worst case scenario, which is called SSP 8.5, could result in over 20 meters of sea level rise spread out over, best guess is about 2,000 years. So 20 meters is let's do the math here. Hold on, I gotta do my not carry the knot. So we're looking at what, 18.6, almost the equivalent of a 7-story building, at the top of the 7th story, right? Or at the 7th story. That's pretty significant. Okay, I'm going to take a little break and then we'll start up again in the second part of this discussion. Need a little water break.